Welcome back, everyone. The approval of cislunar cargo logistics platforms marks a pivotal step toward establishing permanent infrastructure between Earth and the Moon. These platforms are being designed as orbital way stations positioned in cislunar space, the region between our planet and its natural satellite. Their primary role will be to facilitate the transfer, storage, and redirection of cargo needed for moon missions, orbital construction, and deep space expeditions. Unlike traditional one-way launches, this system envisions reusable tugs, cargo containers, and automated docking systems that allow goods to be moved and distributed efficiently in space. Multiple space agencies and private firms have received funding and regulatory clearance to begin building early prototypes. These platforms will reduce the dependency on Earth-based supply chains, opening the path for scalable lunar exploration and economic activity in space. Cislunar cargo logistics platforms will act as orbital hubs strategically placed at locations such as Earth-Moon Lagrange points or low lunar orbit. These hubs will serve as transfer stations where spacecraft can dock, unload, and reload cargo bound for other destinations. The design includes automated docking ports, pressurized compartments for sensitive goods, and robotic arms for handling containers. By establishing permanent nodes in space, operators can break up missions into manageable segments. Instead of launching a single large mission from Earth, smaller payloads can be delivered incrementally to the platform, then bundled and forwarded to their final destination using reusable transport vehicles. The cargo containers used in these operations will be modular and standardized to fit multiple types of vehicles and docking systems. These containers will carry everything from scientific instruments and communication equipment to life support materials and surface construction tools. Each container will include tracking devices, environmental controls if needed, and hardware for robotic manipulation. Robotic systems aboard the platform will sort, inspect, and prepare the cargo for reloading onto outbound missions. This modularity ensures compatibility across different launch providers and enables global coordination of logistics. It also simplifies maintenance and inventory management for future lunar operations. To move cargo between Earth orbit and the cislunar platform, reusable orbital tugs will be deployed. These spacecraft will be powered by high-efficiency propulsion systems, such as electric ion drives or solar electric thrusters. After picking up cargo from Earth-based launches, the tugs will rendezvous with the logistics platform to deliver the payload. Once offloaded, the same tugs can return to Earth orbit for refueling and redeployment. This system allows for a continuous supply chain in space, without the need for expendable vehicles. Reusability is critical for reducing costs and establishing reliable space transport networks. The platforms themselves will be powered primarily by solar arrays, providing energy for all onboard operations, including communication, refrigeration, docking, and robotic handling. Advanced battery systems or fuel cells will store excess energy to ensure functionality during eclipses or equipment surges. Some designs may also include small propulsion units for orbital adjustments or attitude control. Onboard computers will coordinate logistics functions and interface with Earth-based mission control centers. Each platform will include redundant communication links to ensure uninterrupted data transmission with Earth, the Moon, and orbiting spacecraft. One of the critical challenges addressed by these platforms is timing. Launch windows between Earth and the Moon depend on orbital alignments, and cargo delivery must be tightly synchronized to avoid delays. The platforms solve this by acting as holding stations. If a lunar lander or orbiter is delayed, the cargo can be stored at the platform until conditions are optimal for transfer. This introduces flexibility into mission planning and greatly reduces the risk of missing a launch window. It also ensures that cargo arriving from different regions can be consolidated before delivery. To support human exploration, these platforms will also store essential life support resources, such as water, oxygen, and food. These supplies can be stockpiled in advance and delivered to lunar crews as needed. By separating logistics from immediate launch constraints, astronauts can depend on a more stable and redundant supply network. In addition, the platforms can provide temporary shelter or emergency safe zones in case of in-space system failures. Life support modules may be included as part of the infrastructure to provide critical backup for crewed missions transiting the cislunar corridor. Logistics software will play a major role in coordinating all activities associated with these platforms. Real-time inventory tracking, fuel calculations, and traffic management will be handled by intelligent algorithms capable of adjusting plans based on vehicle status, environmental factors, and mission priorities. These systems must coordinate multiple spacecraft arriving from different orbits and launching from various global spaceports. By optimizing schedules and cargo loads, the software reduces downtime and ensures that resources are delivered exactly when and where they are needed. Security and reliability are key priorities for operating in cislunar space. Platforms will be hardened against radiation, micrometeor impacts, and potential cyber threats. Physical shielding, isolated subsystems, and regular diagnostic checks will keep the platform operational even under harsh space conditions. Engineers are also working on maintenance procedures that can be carried out either remotely from Earth or by visiting robotic service vehicles. With such procedures in place, these logistics hubs can remain operational for years without requiring constant human presence. In preparation for full-scale deployment, early prototypes and demonstrations are being developed and tested in low Earth orbit. These trial platforms will validate key technologies such as automated docking, container handling, and orbital station keeping. Lessons learned from these missions will inform final designs for deployment in the cislunar environment. Testing in Earth orbit also enables rapid iteration and problem-solving before committing resources to lunar infrastructure. Once proven, these platforms will be launched and assembled in stages, gradually forming a permanent logistics chain that spans from Earth to the Moon. One promising possibility not yet in development is the use of autonomous cislunar fabrication platforms capable of assembling cargo containers, tools, or even structural components directly in orbit. Instead of launching fully constructed cargo from Earth, raw materials or partially processed inputs could be sent to these orbital factories, where robotic systems would manufacture mission-specific equipment on demand. Such platforms would reduce the cost and complexity of transporting bulky items by enabling customized production in space. They could also recycle spent modules, broken parts, or even debris, converting them into usable goods. While the required additive manufacturing technologies are still advancing, the vision of building rather than launching cargo could eventually redefine how cislunar logistics operate. Another speculative concept involves orbital way stations capable of capturing and redirecting small near-Earth asteroids as a source of construction material and propellant. These natural space resources could be harvested using tether systems or electromagnetic capture methods, then processed at a cislunar refinery platform into oxygen, metals, and water. The materials would be used to supply both lunar and deep space missions, effectively creating a self-sustaining supply chain independent of Earth. Though still theoretical, the integration of asteroid harvesting with cislunar logistics could one day enable permanent habitation and commerce across the Earth-Moon system, leveraging local space resources rather than terrestrial exports. If cislunar logistics platforms are successfully deployed and operational within the next few years, they will become the backbone of space transport beyond low Earth orbit. These platforms could support regular shipments of fuel, construction materials, and life support supplies, reducing launch frequency from Earth and enabling continuous activity around the Moon. They may also be expanded into service hubs for satellite maintenance, spacecraft refueling, or storage depots for emergency supplies. Over time, this infrastructure might evolve into a distributed network, linking Earth, lunar orbit, and surface operations into a unified supply grid. As momentum builds, these systems could make interplanetary logistics possible, not just for governments but also for commercial missions. Thank you very much for watching. Please like and subscribe.